Corey Adams. I'm a staff scientist at ALCF. I'm going to present the TensorFlow profiling tools. If you are in the GitHub repository in 09 profiling frameworks, there's a TensorFlow folder. There's a lot of examples there that we're going to run during this tutorial. I encourage you to follow along. If you have issues with anything, please speak up or put it on the chat. So for profiling TensorFlow, if you see my screen here, we're going to profile again a generative adversarial network. I made some images of the final product. It's an okay GAN. It doesn't do a great job, but there are some passably legible digits it produces. The script that created these is called traingan.py. So if I'm on my Theta GPU node.
Corey, would it be possible to increase the font size?
I'm already doing it. Yes, thank you. Can you see?
I can see, yeah. You may also want to quit your mail so you don't get the notification.
Sure.
Thank you.
Okay, so here we are in the Computational Performance Workshop GitHub, and I have a script, traingan.py. If you run it, and I'll walk you through the script in just a second, we'll get an output after all it starts up, and it will tell us its throughput in terms of images per second. And the first thing we'll have to decide is this good or not? Is this a good performance? Okay, so now it's starting to run. It prints out the this tuple of numbers is the epoch and the iteration, the batch within the epoch. It gives us a generator loss, a discriminator loss. Now, if you're not familiar with the two losses of training a GAN, don't worry. How long it takes to do a step, so just over half a second per iteration, and the throughput, 236 images per second. It runs for one epoch. You can quit it anytime once you've got this. And just to show you where we're going, there's a traingan optimized. You can run this as well, and we'll see after all the optimizations we apply, what's our throughput going to be. Okay, while this is running, let me tell you a little bit about this script. So it's a generative adversarial network. It has two main networks. There's a discriminator here, and there is a generator here. The way a GAN training works is it's a zero-sum game. You train a generator to fake images, and a discriminator classifies them as real or fake. And the better the discriminator, the better the GAN can get trained. Okay, here's the optimized version going. So it's already on epoch 8. The throughput is bouncing around between 140,000 images per second and 100,000 images per second. So that's about 500 times faster. So over the course of the next 25 minutes, I'm going to walk you through all those optimizations to get from the starting point to the end point. So the training script for this is pretty simple. This script starts up and it calls this function traingan with a batch size of however many training epochs it wants. Inside of here, this traingan function, it creates a generator, initializes the generator with some random input. It creates a discriminator, initializes the discriminator with that randomly generated image, and then creates optimizers, Atom and RMS prop, one optimizer for each of the networks, and then it goes through this training loop. Inside this training loop, it just loops over the epochs, and for each epoch, it does this double pass through the networks. It does a forward pass for the generator first, and then it computes the trainable variables, gets the gradient, and applies it. And then it uses the discriminator, forward pass, trainable variables, gradients, apply them. And that's it. This is the GAN training loop. The very first thing we want to do to see what our bottlenecks are is to use Python's line profiler. So if you go into this script, this folder line profiler in the TensorFlow folder, it will have some examples for how you can actually use this. I'm running in a container here. I I put one in the computational performance workshop. I got a more up-to-date container than the one in the README. You are welcome to use this container. This container here will also work just fine. So I run this. If you get these errors, don't worry about them yet. I'll have to check my directory. Okay. The line profiler tool is a simple Python instrumenter. It will look for these decorator functions. If I open the code inside here, it's the same script, but I add some functions at profile. If you're not familiar with decorators, they're a Python syntax that basically replaces a function. It takes a function as an input and gives a function as an output, and it changes it a little bit. So in this case, it's telling Python to decorate this function with profiling hooks so that the line profiler, when it runs this function, will measure how much time each line takes. It's pretty high level. It's only Python calls that get profiled. You don't know anything about what's going on under the hood. So if you're using a library like NumPy, TensorFlow, PyTorch, you don't know any details about its performance. But it does let you identify quickly some high-level bottlenecks. So I decorated 3 functions. I did my main train GAN function. I did the train loop, and I also added the forward pass function up here, which I'll walk through in a second. So to run this, you do kernprof-l. Kernprof is short for kernel profiler. I think it's a Python package. There's installation instructions inside the line profiler. If you're using the same container as me, this one in the computational performance workshop, I pre-installed it, so it's good to go. You do kernprof-l for line, and then you do train-gan.py. So this will run for a few seconds. You'll want to let it get into a few iterations of the training loop. And then at any time, once it's running, you can Control C, and it will still spit out the profiling information after it interrupts the execution. Okay, here it goes. So if you recall, the main script was about 237 images per second. Now we're at 224 to 25. That's expected because profiling does have a little bit of overhead. So we're getting a slightly reduced throughput overall now that we've added the profiling. So this is almost completed in Epoch. I'm going to go ahead and Control C. Gave me this note that it wrote the profile results to train-gan.py.lprof. You can view those very easily with the line profiler module. So if you do Python-m for module line profiler, and then you just pass it this function, this file, it will print out something that looks like this. So it's echoing back my Python code, except now it's giving me these numbers where up here at the header, we can see what it is. So it identifies the line in my file, how many times it hit that line, how long that hit took, as well as the time per hit, and then what's the breakdown in percentage. So it spent about 20% of its execution time initializing the generator. That's okay. That's not much. There's not much we can do to optimize that since that's just startup cost. And then this first pass was also a bit of a hit as it got all the kernels ready on the GPU. And then the rest of the time it's spent in this train loop. So that is about what we expect. Looking at the train loop function, as we scroll through, we see that 88% of the time is in the forward pass. Okay, that seems like it's good. And 10% is in applying calculating the gradients. That's the backward pass of the network. And then just 2% in applying the gradients. If you're familiar with training a neural network, seeing 10% here and 90% here, forward pass versus backward pass, that's a little concerning because the backward pass is usually more computationally intensive. That means to me there's some sort of bottleneck that's not well optimized in the forward pass. Yes, to answer your question, Alfred, on Slack, you do need an interactive QSub for the TensorFlow examples. Okay, so if I look at the results of the forward pass function, here it is. So what's this function doing? It takes in the 2 networks, the generator and the discriminator. It takes in the batch size, and it takes in an input size. So that is part of the GAN. You give it a random number of random numbers. You can determine how many numbers you feed it. That's the input size. Okay, so 92% of this function is in this call fetch real batch. That's getting the real data. So this means that our network is IO bound. The rest of the time, 3.4% of this function is in generating the images, 2% each on discriminating the images. And if that's effectively it, there's very little other time spent in this function. So let me look at this function here, fetch real batch. That one's right above here. It's pretty simple. It gets a train and the test data set, calling this get data set function. It chooses some, it reshapes them and returns them. This get data set function up here, looks to be loading the MNIST data set every iteration. So that's the issue. It makes absolutely no sense to load the data set every time. This is somewhat of a contrived bug. Most people, I think, wouldn't write this code. I wrote it quite poorly to start, so we'd have a good optimization path. But there's a better way to do this. In the same line profiler folder, you can find this function trainGAN_IOFix. Oh my, there we go. It crashed a little bit. Okay, at the top of this function, I've moved the dataset loading up here, and I convert it to tensor. I convert the train data to a tensor. I shuffle it and I make it into a TF dataset. So instead of loading it each time, I'm now just going to be pulling from a dataset. I give it a shuffle, and I change the forward pass function here. Instead of calling get data every time, I just pass it a batch of data. Everything else in here is basically the same. And inside the train loop, I pull a batch of data from the data set each time to give it to the forward pass. So I've now taken all of that IO overhead from loading the MNIST data set every iteration and moved it up front once in a startup cost so that our iterations are much faster. The IO fix is also decorated in the same spots with the profiler hooks. So I can run this same command, kernprof-l train gan iofix.py, and we'll see what we get. So right off the bat, with no changes except to IO, we're running about 10 times faster. All right, so I'll control C that. And I will open this with Python-m line profiler. Okay, so similar distribution here, a little less time starting up the generator, a little more time the first time through. Still spending most of our time in train loop. Again, that's kind of what we wanted. Now when I look at this train loop function, getting the data set is very quick to shuffle. Pulling the data, not so bad. And then half my time in the forward pass and about a third of my time in the backward pass. So we're getting much closer to an optimized and balanced implementation here. This right here, 45% in our forward pass. If you look at this, most of our time is still spent in the generator, the discriminator, both times. So that's 40% plus 25 plus 25 is 90% of our forward pass is in these three calls. And then just a little bit in these loss computations. In TensorFlow, the way that a network is run in eager mode is it will actually call a Python function, and it will go through, for example, this one is the generator. Yes, so it will take inputs and it will go through these loops. And each time it finishes an operation, it goes back to Python, goes through some control statements to get to the next layer. It goes back down into the CUDA kernels, runs your layer on your GPU, and comes back to Python. You can optimize that in Python or in TensorFlow through the TF function interface. So this is what we'll do next. If you're following along on an interactive node, head back up to the main folder and go into this TF function folder. Okay, so I have the same implementation that we fixed with the IO in here, but now I have these decorators. At TF function. So this is a TensorFlow syntax. just like the profiling hook was a decorator and took in a function and returned a function, this is doing the same thing, but this is telling TensorFlow, the first time you go through this function, trace everything that happens, and instead of going back to Python for each subsequent call, just make a graph, a TensorFlow graph, so that you take the inputs, do all of these operations within TensorFlow's C++ API, and then give you back the outputs in Python. And these get nested. So I put one on the discriminator, I put one on the generator, their call functions, which is where they're actually computing. I put one on the loss function, and I put it on the forward pass. Now here's a detail that's a little tricky. The forward pass I had before used some NumPy operations, for example, generating random data, creating zeros and ones. All of this has to be converted to TensorFlow operations, because if you leave them as NumPy, they'll get called once on their first pass through TensorFlow, and then that output gets saved as a constant. So if you're doing random numbers, that's quite bad. You'll get terrible results. You need to convert these to TensorFlow. Each time it goes through, it will nest this. So if I hadn't put something on the discriminator and the generator, it actually doesn't matter. TensorFlow will try to apply TF function to everything within this function that you've decorated. The last thing I did is in the train loop, I made this training iteration into its own function. So this function is within the context of the other function. So it only exists inside this train loop context, but it's called train iteration. It takes the data, models the optimizers and the global size if it's data parallel. And this is so I can do the forward pass, the gradient calculation, and the gradient application together. TensorFlow doesn't like the loop I had over that list of strings, network, generator, and discriminator. So I just broke that into two pieces, update the generator, update the discriminator. And this can be compiled, graph compiled with TensorFlow. And then the actual training loop looks like this. So it calls this train iteration each time, gets the loss, and then goes on to the next match. So if you're doing this, you can run Python train-gan IOFix, and we'll see how we're doing. The graph compilation typically takes a few iterations to really get up to speed. So there it goes. Now we're running at 89,000 images per second for the first epoch. That's quite fast. One thing that we can add to do an additional compilation in TensorFlow is once you've reached the graph optimization level where you've reached, you've compiled a function, TensorFlow has a tool called XLA, and you can find the syntax for this in the README for this folder. But you can add an environment variable, tf XLA flags equals this. So I'll export that. And that will take every graph compiled function and try to fuse operations. So if you have a convolution followed by an activation, it can actually fuse them into one operation, conv plus activation, run it on the GPU, and you'll get better performance because it doesn't have to do any memory access in between those operations. The downside of XLA is you will lose sight of some of your profiling operations. When we profile with XLA, it just shows up as an XLA kernel, versus if you profile without XLA, you'll be able to identify conv2D, etc. With XLA applied, we got another 10,000 images per second. So that's a nice boost. I'm going to switch folders again and look at the TF profiler folder. So this is the same code as before, but now it has an additional line. Here we go. Down in the train loop, I've added two lines, tf.profiler.experimental start, and then at the very end, tf.profiler.experimental stop. This is the TensorFlow built-in profiler, and it will give us the, similar to PyTorch's profiling, it will actually look at call by call, what's going on under the hood in terms of CUDA operations, TensorFlow operations, and let us see a little more clearly into the problem. If you're not following along, some of these results are on the GitHub. So this TF profiler folder has some screenshots of what the TensorFlow profiler looks like. So you'll land on a splash page of performance summary, and it will give you some recommendations for the next step. Some of these are useful, some of these are not. 3.3% of the total time is actually spent on kernel launch. That's because we generally have a very small network here. This GAN is quite small compared to what the A100 can do. This tidbit here, only 0.0% of device computation is 16-bit. That's actually an important one. It's telling us we're in float 32 precision. If we went to float 16, we could get a significant speed up, it says, if the reduced accuracy is acceptable. When reduced precision is and isn't acceptable, we'll actually hear about in the next talk. As you scroll down, it gives you the list of the top 10 TensorFlow implementations. Without XLA, you'll see the actual calls, so conv2d backprop filter, and you can look at the operation and see, okay, this is conv2d_2. That's the second convolution that it was called. Here's the first one. There's a batch normalization. There's another conv2d_5, and they're all roughly equal in time, which is what we want. And they're stacking up to account for 25% of the total time is in these top 10 operations. So it looks like we have a lot of fairly small operations. Again, if you go to the kernel statistics page, you see a pretty even distribution. Just like PyTorch, TensorFlow Profiler has this timeline view. It'll be a little less divided if you use XLA, because you'll just see a couple XLA blocks. But you can even zoom in and see here's a full iteration. On the top is the GPU, on the bottom is the CPU. You can see this chunk. If you see my mouse, this is doing our data loading, and then it jumps over to the GPU and does our forward and backward pass. It does the generator and then the discriminator, and then it finishes the iteration and goes on to the next one. So the last thing I want to try with you is in reduced precision. There's a pretty easy way to get to reduced precision in TensorFlow. You can make this call before you actually run anything. tf.keras.mixedprecision.setGlobalPolicy, and then you can say mixed float 16. In my script, due to the way I wrote it, which isn't necessarily the perfect way, there's a couple of float 32 ops that have to be changed to float 16. That's pretty easy to control F, find them all and fix them. If you're running in the original container I had for this, which was from February, you actually see a slowdown. And if you do the profiling, it's pretty quick to find out why. One particular convolution takes 25 to 26% of the time. So we no longer have an even breakdown, but you get one big op slowing everything down. And when you zoom into the trace view, you can see it right here. It's this massive conv2d_3. That's actually a bug. If you run in the latest container, this goes away. So giving you better FP16 precision is actually fixed in the latest version. Okay, so putting it all together, this train GAN optimized is including all of these optimizations we did. So it's got the data set loading up here. I set the XLA environment variable in the file, so it's always on. I apply all my TF function operations, and I, right here, set my mixed precision policy. So it's using float 16, and I changed all my float 32s to float 16 everywhere. So they're all fixed. And that's how you end up with going from, say, 230 images per second to 140,000 images per second. I'm going to leave time for a few questions, but I'll just throw it out there. There's an inference version of this script as well that doesn't do the backpropagation and includes all these same optimizations, which will get you for inference level up to about 400 to 500 images, 400 to 500,000 images per second in inference. This model is small and the image size is small. So one of the other optimizations you can do is increase the batch size, which in the optimized version I do. The batch size is up to more than 8,000. It's still a very small load on the A100 GPU. But this is just one example of how you can take some of your TensorFlow code and really accelerate it. So I'll leave time for a couple questions, either to me or Dennis, I think is fine.